Hello everyone, welcome to my CE4 video presentation. Today I will present on the topic of permutation matrices and explain my solution for the CE3 programming assignment. First, in part 1, I will provide the background knowledge comparing general matrices with permutation matrices. Then in part 2, I will walk you through my CE3 task which focuses on finding proper square roots of the identity matrix. Let's start with the history. Matrices are the fundamental language of linear algebra, formalized by Arthur Clay in 1858. However, the concept of permutations existed much earlier in group theory, studied by Cauchy and Glauer. The permutation matrix is historically significant because it serves as a bridge between these two worlds. It translates the abstract logic of reordering into the calculation language of matrices. So, what exactly is a permutation matrix? A standard matrix is simply a grid of numbers. A permutation matrix, however, is a special square binary matrix. It contains only ones and zeros. The rule is strict. There must be exactly one 1 in each column and each row. You can think of it as an identity matrix that has been scrambled. Then how does it work? It shuffles the data without changing their values. As shown in the example, if we multiply a matrix A by P on the right, it reorders the columns. While if we multiply on the left, it reorders the rows. And the most powerful property of permutation matrices is their inversion. Normally, calculating the inverse of a matrix is a slow and complex process, but because permutation matrices are orthogonal, their inverse is simply their transpose. To undo a shuffle, we don't need complex algorithms. We just flip the matrix along the diagonal. This is incredibly efficient. Let's verify this to see why it works. Let's focus on the identity matrix first. To get the top left 1, we must multiply the first row of the inverse by the first column of P. So to get a dot product of 1, the inverse first row must have a 1 at the third position. Following the same logic for the second and third row, we can see the patterns clearly. The columns of the inverse adjust the rows of P. This proves that the inverse is indeed the transpose. Finally, why do we care it? Because these matrices are used in many fields. In computer graphics, they are used to transform objects. In linear algebra, they help solve equations efficiently by pivoting. They are even used in quantum mechanics and data analysis to organize and process complex structures. Now that we have covered the mathematical background, let's move on to the part 2, the CE3 task. The goal of my assignment was to write a Python program to compute the number of proper square roots of the identity matrix. Mathematically, I needed to find permutation matrices P such that P squared equals the identity matrix, but P is not the identity matrix itself. And the constraint was to calculate this for size up to 20. For n equals 20, brute force checking will be impossible because the number of permutations is huge. So I used a mathematical strategy. A permutation matrix squared equals to identity if and only if it is an involution. This means the permutation must consist only of 1 cycles and 2 cycles. So I derived a formula based on 4 steps. First, if we have key transpositions, we must choose 2 key elements from the total n to participate in these swaps. Next, we partition these elements into pairs. Crucially, we divide by key factory. This is because the order of key transpositions doesn't matter. We then sum up these calculations for all possible numbers of swaps from 0 up to n over 2. Finally, the result includes the identity matrix. Since we need proper rules, we subtract 1 to exclude it. We can also understand this logic using a recursive relation. For any element n, there are only 2 cases in an involution. In case A, n stays in place. We then look at the remaining n-1 elements. And in case B, n swaps with another element. There are n-1 choices for a partner, and we look at the remaining n-2 elements. This logic leads to the total count formula. Finally, we subtract 1 to exclude the identity matrix. Based on this math, here is my code design. The input is the integer n, the size of the matrix, and the output is the total count of proper square roots. In the code, the key variable key represents the number of 2 cycles in the permutation, and S is the total count accumulator. And here is the Python implementation. The logic is straightforward and efficient. To start, I iterate through all possible numbers of swaps key. Inside this loop, for each key, I compute the specific combinations using the factorial formula. Then I add this result to our running total S. Finally, once the loop is complete, I subtract 1 from the total. This crucial last step ensures we exclude the identity matrix, leaving us with only the proper square roots. This concludes my presentation. By bridging the concept of involutions with matrix theory, I was able to create an efficient solution for the task. Thank you for watching.